Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to address a question asked by one of the viewers of my YouTube channel. So in this question, it is asking you to find the stationary points on the graph of this given function here. So in order to find the stationary points, our first step is to find what is the derivative of this function here. So what is dy dx? So dy dx, according to the function given here, is going to be equal to 3x squared, and if you differentiate this, it will be negative 6x, and if you differentiate the constant, it's going to be equal to 0. Next, if you want, you can write it in the simpler form, or maybe you can factor the terms here. So you will have 3x x minus 2. So you can see that if you multiply 3x with x, you will get back 3x squared, and if you multiply 3x with negative 2, you will get back negative 6x. So the stationary points are the values of x, okay, the values of x such that, so I'm just using the short form here, st means such that, so values of x such that the first derivative is equal to 0, and so we are going to set dy dx equals to 0. So when dy dx equals to 0, therefore 3x x minus 2 is going to be equal to 0. And in this situation, we have two scenarios to consider. So the first one here is we are going to consider 3x equals to 0, and therefore x must be equal to 0. So this is the first solution. And the next scenario is we're going to consider x minus 2 equals to 0, and therefore x must be equals to 2. So these are the stationary points which are asked by the first question here. Next, the question is asking you to distinguish between them. Basically, you are required to give a label to these points here, whether there are local maxima or local minima, or perhaps point of inflection. Alright, so in order to distinguish the points given here, I'm going to consider creating a table which contains some of the intervals of interest, and I'm going to see the behavior of dy dx. Okay, right. So here is the table of interest. So I'm going to construct the interval. So the interval here is based on these important points, x equals to 0 or x equals to 2, and the interval begins with finding or considering the values of x being less than 0, and the next one is x between 0 and 2, and finally we are considering the interval of x greater than 2. And then based on the result that we've got here, which is the first derivative, we are going to consider two factors here. So the first one is 3x, and the next column is going to be dedicated to x minus 2, and then the last column here is going to talk about the behavior of the first derivative, which is f prime x or dy dx. So now when x is less than 0, you can think of any number which is easy for you to compute. So for example, if x is negative 1, let's say, you will see that if you plug in negative 1 next to 3, you will get that the sign of this is going to be a negative sign. And if you consider negative 1 minus 2, the sign is also going to be negative. And so if you multiply 3x with x minus 2, you multiply these two factors here, the sign is going to be a positive sign. Next, if you consider any value of x between the interval of 0 and 2, for example 1, let's say. So here is going to be a positive sign, and 1 minus 2 is going to be a negative sign. So here we go, we've got negative sign. So if you multiply these two factors here, the answer is going to be negative. Next, if you consider any value such that x is greater than 2, for example 3, so here is going to be a positive value. Over here is also going to be a positive value. So therefore, the sign of our first derivative, dy dx, or f prime x here is going to be positive. Okay, so based on the signs given here, we can come up with the label of our stationary points, whether they are local max or local minimum. So what we can do is, first of all, we are going to check x equals to 0. So I'm going just to consider the simple line here. This is at point x equals to 0. Okay, so here we have the area of x being less than 0. So x being less than 0 is this area, x being less than 0. Next we have this part here where x is being greater than 0. Okay, immediately after 0 will be the area of x greater than 0. And when you look at this, behavior of the first derivative, which is basically the first derivative is also gradient or slope, and if you get positive value, that means the behavior of this function, it is increasing in nature. So the slope is going upwards from the left direction to the right direction. So you can imagine that we have a slope that is a positive slope going towards x equals to 0. So this is what's going on here. And for x being greater than 0, the gradient is negative, which means after x equals to 0, it is going downwards. So based on this, you can see that at x equals to 0, the point here is a local maximum point. Okay, so local max. Okay, so now let's consider the next point, which is x equals to 2. So this is at point x equals to 2, and we are going to consider the area here. So x equals to 2. So this is the area where x is less than 2, and this is the area that x is greater than 2. So based on this table of interval that we have here, x being less than 2 is this one. So you can see that the gradient is negative. Therefore, we know that it is going downwards. Okay, this is going downwards towards x equals to 2. This is what you can imagine. The gradient is negative. And for x greater than 2, the gradient is positive. So that means it's going upwards. And based on this, clearly you can see that at x equals to 2, this is the point of local minimum. Okay, so that is one way to distinguish whether the point that you have found is local max or local minimum. Now, the next question is asking you to find the point of inflection, if there's any. So what is the point of inflection? So in order to find the point of inflection, you need to see what are the values of x. What are the values of x such that the second derivative is equal to 0. So we need to find what are the values of x such that the second derivative is equal to 0. And in order to be the point of inflection, there must be changes in the sign of the second derivative. Okay, there must be the changes in the sign of second derivative, and this is going to be illustrated shortly. Okay, just bear with me. All right, so now we are going to start off finding the point of inflection with differentiating this once again. Okay, so we're going to differentiate that. So therefore we're going to find the second derivative is going to be equal to, differentiate this once again. So we're going to differentiate the result of the first derivative here. So 3x squared minus 6x. And if you differentiate this, it's going to be equal to 6x minus 6. And if you want, you can factor 6 out. So 6 and x minus 1. Okay, so that's the first step, which is to find the second derivative. And if you want to find what is the point of inflection, okay, like I said earlier, there are two parts that you need to do. First one, you need to find, is there any value of x such that this is true? And second, you must make sure that at that particular point, there are changes in the sign of the second derivative. Okay, so we're going to do the first step now. We're going to set this equal to 0. So the second derivative is equal to 0, which then leads us to have 6x minus 1 equals to 0. And based on this, we know that x must be equal to 1. So this could be the point of inflection, but then we have to check whether there are changes in the sign of the second derivative or not. So for that purpose, I'm going to just construct a simple table. So the table here contains the interval of interest, and it also contains the given factors here, which is 6, x minus 1. And we are going to check the behavior of the second derivative, which is f double prime x. Now, since the point here is only one point, x equals to 1, therefore we are interested to find what is going on when x being less than 1 and what is going on when x is greater than 1. So for this purpose, again, you can choose. For example, if x less than 1, you can pick any value which you think is easier to be computed. For example, -1. So when x is -1, this one is not a factor at all. It remains a positive value. So x -1, the sign here is going to be negative. And therefore, we have a negative sign. When you multiply these two factors together, you will have a negative sign. Now for x greater than 1, you can choose any value, for example 2. So this one is going to be positive. 2 minus 1 is also going to be positive. So therefore, when you multiply the two factors here, the behavior of the second derivative is going to be positive. So you can see that there are changes in the sign. So at point x equals to 0, so this is point x equals to 0. Sorry, x equals to 1, I'm sorry. At point x equals to 1, for the area of x less than 1 and the area of x greater than 1, there are changes in the sign. For example, for this area, the sign is negative, and for this part here, the sign is positive. So that's what that is the meaning of the statement given here. And because of that, we can say that x equals to 1 is the point of inflection. So this is the point of inflection. Okay. All right. Okay, so what does it mean when you get a negative result over here? That means the graph is concave downward. And when you get the positive result, means the graph is concave upward. Okay, I think that's all for now. Thank you very much for watching.